In this question, a scientist has a sample of a 0.203 molar solution of a fictional weak acid with the formula HRE2 that has a pH of 3.73 at 25 degrees C. Here's our equation. HRE2 loses one H plus ion to become Re2 minus. Our first step is to complete the ice table for the dissociation of this acid. Now we're told that the sample has a 0.203 molar concentration. So that's going to be the concentration of HRE2 at the beginning, initial. And when we first add it, none of it is dissociated. The acid will then dissociate until it reaches the equilibrium concentrations, which is what we're trying to find. So we're going to fill this ice table in exactly the same way as we have in the previous units. So for our change, we're going to use X, and we're going to look at our equation and figure out what the changes of each compound would be in terms of X. So if we use up X of HRE2, we're going to have a change of minus X. And that means we're going to have a change for our products of plus X. Because for every HRE2 that's used up, we make an H plus and an Re2 minus. So those are going to be our changes in concentration. And then for our equilibrium concentrations, all we have to do is add our initial and our change together. So it's going to be 0.203 minus X. It's going to be 0 plus X, which is just X, and 0 plus X, which is just X. So that's our information so far. We've also been told in the question that the pH of the solution is 3.73. So we can use the definition of pH to figure out the concentration of the H plus ions. Let's head to the reference sheet. Here's our pH equation. pH is negative log of the concentration of H plus. pH is negative log the concentration of H plus. So we know pH, and we're trying to find the concentration of H plus because that is in this column of our ice table here. So let's rearrange this equation for the concentration of H plus. First, I'm going to multiply both sides by -1 to get rid of that minus sign on the right. Then I'm going to do 10 to the power of, because the inverse function of log is 10 to the power of. So we've got 10 to the power of negative pH is equal to 10 to the power of log the concentration of H plus. And 10 to the power of and log cancel to give us 10 to the power of negative pH is equal to the concentration of H plus. Okay, so we're ready to put our numbers in. So to get the concentration of H plus, it's 10 to the power of negative pH, 10 to the power of negative, our pH is 3.73 from the question. So if we put that into our calculator, that gets us a concentration of H plus ions of 0.000186 molar. So that is our equilibrium concentration of H plus. And if we look here, the expression for the equilibrium concentration of H plus is just X. So that means that X is 0.000186 molar. So now we know X, we can go ahead and fill everything in our table. So here our change is going to be negative 0.000186. Here our change is going to be positive 0.000186. And the same here, positive 0.000186. That leaves us with both the H plus and Re2 minus concentrations will be 0.000186. Now for the equilibrium concentration of HER2, we can see that our X is much smaller than our initial concentration. So actually we can just ignore that negative X. We're using the small x approximation, which basically says that if X is small enough, it doesn't make any difference when it's added to a larger value. If we wanted to, we could do 0.203 minus 0.000186. But when we round that to three significant figures, we're just going to get 0.203. So that shows us that our small x approximation works in this case. So our answer here is just going to be the same as our initial concentration, 0.203, because the change was so small it doesn't actually affect our value. Okay, awesome. So we use the pH to find the concentration of H+, and we use that to fill out our ice table. Next, we need to find the percent ionization of HRE2 in this solution. So let's head to the reference sheet to find an equation for that. Here's our equation for percent ionization. The percent ionization of an acid is 100 times the concentration of H+ ions divided by the concentration of HA, which represents the acid itself. So percent ionization of an acid is equal to 100 times the concentration of H+ ions divided by the concentration of the acid itself. HA represents a general acid. Here our acid is HRE2. So I'm going to change the HA to say HRE2 because that's a specific acid we have in this question. So we can go ahead and put on numbers. We've got 100 times the equilibrium concentration of H+, which is 0.000186, divided by the equilibrium concentration of HRE2, which is 0.203. So if we put that into our calculator, we're going to get a percent ionization of 0.0917%. Awesome. So let's go ahead and fill that in over here. And let's think about that for a second. We know we have a weak acid, and we can see here, oh, it is weak. We only have 0.09% of the acid that actually dissociates into its ions at 25 degrees C. Okay, our last step is going to be finding our acid dissociation constant. Let's head to our reference sheet. Here's the acid dissociation constant. Ka is equal to the concentration of H+ times the concentration of A- divided by the concentration of HA. And remember, HA represents a general acid, and A- would represent the conjugate base of that acid. So we can fill in with the actual acid we have in our question and the actual conjugate base. So instead of A-, we'll have our conjugate base, which is Re2-. And instead of HA, we'll have our acid, which was HRE2. So we have this shortcut equation that we just used, but you'll notice this is just the equilibrium constant for this equation. We've got our products on the top, which is H+ and Re2-. We've got our reactants on the bottom, which is HRE2. All of them have a coefficient of 1, which means all of them are just to the power of 1, or in other words, we don't need a power on them in the equation. So the acid dissociation constant is the equilibrium constant for an acid dissociating. Okay, we can go ahead and fill these in now. So we've got H+ and Re2- on the top and HRE2 on the bottom. Awesome. Okay, so final step is calculating our acid dissociation constant. Well, we know the concentrations of all of our species at equilibrium from the equilibrium concentration row in our ice table. So we can go ahead and fill that in now. For H+, it's 0.000186. For Re2-, it's also 0.000186. And we'll divide that by the concentration of HRE2, which is 0.203. So if we put that into our calculator, we're going to get a Ka value of 1.71 times 10 to the power of -7. So let's go ahead and fill that in. 1.71. Remember, on this platform, we write E instead of times 10 to the power of -7. Awesome. Again, you can see this is a really tiny number, much less than 1. That's telling us our reactants are highly favored at equilibrium, which makes sense because it's a weak acid and we know that only 0.09% of it ionizes into its ions. So that all matches up and makes sense logically.